Let's look at the expression, the limit of x squared minus 2x as x approaches 3. Now, of course, we don't want x to equal 3 here, but let's cheat again and see what this thing means. Our intuition tells us that when x is 3, x squared is 9, 2x is 6, so 9 minus 6 is 3, and we would suspect that the limit here should be 3. Now, to see what this means, let's draw a little diagram. The graph y equals x squared minus 2x crosses the x-axis at 0 and 2. It has its low point at the point 1 comma minus 1. See, we can sketch these curves. It's a parabola. And now what we're saying is it true that when x gets very close to 3, is it true that when x gets very close to 3, that f of x gets very close to 3? And the answer is, from the diagram, it appears very obvious that this is the case. In fact, here's that example of non-single valued again. If you call this thing L, and you now pick tolerance limits, which we'll call L plus epsilon and L minus epsilon, and now you want to see what interval you need on the x-axis, notice that in this particular diagram, you will get two intervals, one of which surrounds the value x equals minus 1, and the other of which surrounds the x value x equals 3. In other words, both when x is minus 1 and x is 3, x squared minus 2x will equal 3. See? At any rate, leaving the diagram as an aid, let's see what our epsilon delta definition says and how we handle this stuff algebraically and how we correlate the algebra with the geometry. Given epsilon greater than 0, what must I do? I must find a delta greater than 0 such that when, and I'm going to read this colloquially, I'll write it formally, but read it colloquially, such that whenever x is within delta of 3, but not equal to 3, then x squared minus 2x will be within epsilon of 3. Now here's the whole point. We know algebraically how to handle absolute values. Namely, the absolute value of x squared minus 2x minus 3 being less than epsilon is the same as saying that x squared minus 2x minus 3 itself must be between epsilon and minus epsilon. Now again, we rewrite things in fancy ways if we wish. There are other ways of doing this. I call this completing the square. Well, people for 2,000 years have called this completing the square. Namely, I rewrite minus 3 as 1 minus 4, so that x squared minus 2x plus 1 can be factored as x minus 1 squared. I'm now down to this form here. Then I add 4 to all sides of my inequality and have that x minus 1 squared is between 4 plus epsilon and 4 minus epsilon. Some fairly elementary algebra of inequalities here. Now here's the key point. Remember in my diagram I said to you, how do we know whether we're near 3 or near minus 1? How do we distinguish when we draw the lines to the curve what neighborhood we want? And notice that all we're saying is that if x is near 3, that means what? X is close to 3? If x is reasonably close to 3, then x minus 1 is going to be reasonably close to 2 and hence be positive. Point is that as long as you're dealing with positive numbers over here, see if epsilon is sufficiently small, these will then all be positive numbers. For positive numbers, if the squares obey a certain inequality, the square roots will obey the same inequality, as we have emphasized in one of our exercises. In other words, from here, we can now say this. And from this, we can now conclude that if you want x squared minus 2x to be with an epsilon of 3, x itself is going to have to be between 1 plus the square root of 4 plus epsilon and 1 plus the square root of 4 minus epsilon. And by the way, this is quite rigorous, but I don't think it turns you on. I don't think there's any picture that you associate with this. And so what I thought I'd like to do for our next little thing is to come back to our diagram here and show you what this really means. Namely, notice that if epsilon is a small positive number, let's take a look at this again. If epsilon is a small positive number, this is slightly less than 4. Therefore, the square root is slightly less than 2. Therefore, this number will be slightly less than 3. On the other hand, 4 plus epsilon is slightly more than 4, so its square root will be slightly more than 2, and therefore 1 plus that square root will be slightly more than 3. And what these two numbers, as abstract as they look like, correspond to is nothing more than this. Coming back to our diagram and choosing an epsilon, and coming over to the curve like this, and projecting down like this. All we're saying is, see, what are we saying pictorially? That for f of x to be within epsilon of L, x itself has to be in this range here. And all this says is that if this very simple point to compute, just by projecting down like this, its rigorous name would be 1 plus the square root of 4 minus epsilon. That's this number over here. And the furthest point, namely this point here, which again, in terms of the picture, is very easy to find, that point corresponds to 1 plus the square root of 4 plus epsilon. And again, notice, in terms of the algebra, I need no recourse to a picture, but in terms of the picture, I get a heck of a good feeling as to what these abstract symbols are telling me. Well, let's continue on with the solution of this exercise. You see, we didn't want to find where x was. We wanted to see where x minus 3 had to be. In other words, we're trying to find the delta. We know that x minus 3 is between these two extremes here. Consequently, and here's the place we have to be a little bit careful here, this, of course, is a positive number because this is more than 2. This, on the other hand, is a negative number because you see 4 minus epsilon is less than 4, so its square root is less than 2. You see, so if I subtract 2 from it, it's a negative number. And since delta has to be positive, if this thing is negative, 2 minus the square root of 4 minus epsilon will be positive. So what I do is, to solve this problem, is I simply choose delta to be the minimum of these two numbers. And then, by definition, what do I have? That when the absolute value of x minus 3 is less than delta, and at the same time, this is crucial, greater than 0, in other words, we never let x equal 3, for this choice of delta, by how we work backwards, this will come out to be less than epsilon. And that is exactly what you mean by our formal definition of saying that the limit of x squared minus 2x as x approaches 3, in this case, equals 3. For someone who wants more concrete evidence, I think all one has to do is, for example, take a number like 1 plus the square root of 4 plus epsilon. That is the widest point on our interval. And actually plug that in for x. And go through this computation of squaring 1 plus the square root of 4 plus epsilon. Subtract twice 1 plus the square root of 4 plus epsilon. Carry out that computation, and you get what? 3 plus epsilon. That using the upper extreme, you wind up with what? In excess of 3 by epsilon. Which, by the way, is exactly what's supposed to happen. In fact, I hope this doesn't give you an eyesore. I will pull down the top board again to show you also what these two distances mean and what this means. You see, all these two numbers mean is the following. And I'll pull this down just far enough to see it. That these two numbers were the widths from this endpoint to 3 on the one extreme, and from this endpoint to 3 on the other extreme. In other words, those two numbers that we took the minimum of were the half-width intervals that surrounded 3. You see, the problem, as we mentioned before, is that even though epsilon and minus epsilon are symmetric with respect to L, when you translate over to the curve, because this curve is not a straight line, when you project down, these two widths will not be equal. And by picking the minimum of these two widths, you guarantee that you have locked yourself inside the required area. You see, that's all this particular thing means. Now, the trouble is that one might now get the idea that there are no shorter ways of doing the same problem. You see, I showed you a rigorous way. There was no law that said we had to find the biggest delta. In other words, if delta equals a half will work, in other words, if you're within a half of 3, something's going to happen, then certainly any smaller number will work just as well. right? In other words, I can get estimates. Let me show you what I mean by that. See, another way of tackling how to make x squared minus 2x minus 3 smaller than epsilon is to use our properties of absolute values and to factor this. In other words, we know that x squared minus 2x minus 3 is x minus 3 times x plus 1. We know that the absolute value of a product is the product of the absolute values, so these two things here are synonyms. Then we know that near x equals 3, which we're interested in here, x plus 1 is near 4. Well, what we mean more rigorously is this. Choose an epsilon, and if the absolute value of x minus 3 is less than epsilon, in other words, if x minus 3 is less than epsilon but greater than minus epsilon, then by adding on 4 to all three sides of the inequality here, we see that x plus 1 is less than 4 plus epsilon but greater than 4 minus epsilon. Now you see, if we simply assume that epsilon is less than 1 in magnitude, see, if epsilon, an absolute value, if the size of epsilon is less than 1, then certainly this is less than 5 and this is greater than 3. Now, of course, somebody may say to us, but what if epsilon is more than 1? Well, obviously, if a guy says, make this thing within 10, and I can make it within 1, certainly within 10 is within 1. I can always pick this smaller number. I mean, it's like that nonsense of the fellow asking for an ice cream cone, and the waitress said, what flavor? And he said, anything except chocolate. And she said, I'm all out of chocolate. Will you take anything except vanilla? I mean, the idea is that if somebody says, make this less than 15, if you've made it less than 10, in particular, you've made it less than 15. And so all we do over here, you see, is something like this. We say, look, if we want to make this number here very small, we know that this number here is less than 5. We know that epsilon over 5 is a positive number if epsilon is small. So why don't we just pick the absolute value of x minus 3 to be less than epsilon over 5? In fact, that's what this delta will be in that case. In other words, if the absolute value of x minus 3 is within epsilon over 5 of 3, see, if x is within epsilon over 5 of 3, notice what this product becomes. This is less than epsilon over 5. This we know from before is less than 5, and therefore this product is less than epsilon. In other words, we have exhibited the delta such that when this happens, the absolute value of what we want to make less than epsilon indeed becomes less than epsilon. Now, because I recognize